So we've reached the final week of the course, and we're going to finish off what we started last week, which was looking at linear systems of DEs. What we still have left to do is we need to figure out how to solve linear DE systems that are non-homogeneous. And in fact, we have lots of methods that we can do, and they're going to look quite familiar. So we're going to look at using the Laplace transform, we're going to look at using undetermined coefficients, and then finally we're going to introduce the idea of the matrix exponential, which is also going to look extremely familiar, and really will draw the parallels between the single DE case and the system DE case very nicely. Okay, so obviously one of the first things we could do, pretty straightforwardly, is simply take the Laplace transform of our system. So just so that we're all on the same page, we are looking at systems of first order linear DEs. In this case, they are non-homogeneous. So just so that you kind of have a clear idea in your head of exactly what this matrix equation is, it's something like, for example, the first derivative of x1 is equal to some constant times x1 plus some constant times x2. Remember, each of these x's is a function of time. And we have, so that should be an a. So we have n of them, so that's xn of t plus, and then we have some explicit function of t. That's our first differential equation. Our second one is talking about the rate of change of x2, so we've got an x2 of x1 of t, and so on. And you finally have your last equation will be for xn. And we packed all those differential equations. We took out the coefficients into the a. We said that this x over here is x1, x2, x3, blah, blah, blah. And we pulled all the f's out into here. And we turned this into a column vector over there. And so we pack all those crazy differential equations, all n of them, into this one neat differential equation that we've got over here. So there's a lot of information in this differential equation. But it is really just n differential equations, so there's no reason why we can't just take the Laplace transform of each of those. So if you think about what happens if you take the Laplace transform of, for example, this first equation here, we know that x1 first derivative with respect to time, if we take the Laplacian of that, if we take the Laplace transform of that, then we get s x1 of t minus x1 at 0. And then that's going to be equal to, and then remember, so we're thinking about the Laplace transform now of the right hand side here. The Laplace transform is linear, so we can take out the constants. So you'd have a11 times the Laplace transform of x, so this should be an s here, sorry, there should be an s here, plus a12 times the Laplace transform of x2, and so on. And then finally you'd get the Laplace transform of your f1, so that would be a big F1 of s. And you'd get n of those for each of your original differential equations. And by playing the same trick of turning, for example, all the big x's into a single column vector, all these constants here into a column vector, we can write our Laplace transformed version of our matrix equation as this matrix equation here. So noting that our big X here is each component is the Laplace transform of each of our original functions that we had, our little x1, x2, x, so on. And our big F here is the Laplace transform of each of our F components. Okay. So with a little bit of rewriting, we can get our equation here into this form. So if you want to have a look at what we've got, we've taken this ax over to the right hand side. So we have s x of s minus ax of s, and we've taken our x naught over to the other side, so that's going to be f of s plus x naught. And then, so this s over here, remember, is a scalar, but we can just as well write S, our scalar, times X as S times the identity matrix times X of S. So that's just like multiplying by 1, except we've multiplied by the identity matrix. And once we've got this left-hand side in this form over here, we can take out, we've got an SI, which is a matrix. It's the identity matrix, just with S on the diagonal, because we multiplied everything by S. And we've got this A over here, so we can take out this matrix over here, and that's how we end up with 6.33. So this is just a matrix equation. We've got a system of n linear equations in n unknowns. Here our n unknowns are these big x's here, our Laplace transforms of our little x's of t's. And so you can just plug it into any matrix algebra system. So MATLAB would do it for you, Wolfram Alpha will do it for you. And so you can solve for your big x1, big x2, and so on. So you end up with your Laplace transforms. And then for each of those, we already know how to inverse Laplace transform. We've already been doing that. And so you can end up with your xk. The advantage to using this particular technique, as we saw when we were dealing with individual differential equations, is we don't have very many constraints on the non-homogeneous part here. We can use discontinuous and impulsive driving functions. So this is a pretty general technique that we can use. So although there's a whole lot of matrix algebra going on, we're really just extending exactly what we did in the single DE case. So let's have a look at an example. It's going to take us a little while to work through it. So this is a kind of a typical differential equation problem that crops up in things like chemical plants, where you're trying to work out concentrations of things being mixed. So here we've got two tanks. We've got this tank and this tank, and they're going to both start filled with pure water. And what's going to happen is we're going to pump some salt water into each tank. Well, we're going to pump water into tank 1, which contains some salt. So it's going to pump at a rate of 5 liters per minute, and the water that pumps in is going to have a concentration of 0.1 kilograms of salt per liter. Okay. And at the other end, we're going to pump water out of our tank 2, and it's going to be at the same rate that it pumped in. So we're not going to have a build-up of water in either of our tanks. The same amount goes in as the same amount as goes out. But we've also got a situation where we're trying to mix the water in these two tanks. So we're going to pump water, the salt mixture that is, from tank 1 to tank 2 at a rate of 8 liters per minute, and it's going to go back at a 3 liters per minute from tank 2 to tank 1. And what we want to find out is we want to be able to model the amount of salt. So x1 is going to denote the amount of salt in tank 1 at time t, and x2 of t is going to be the amount of salt in tank 2. And because we start with pure water, but then we start pumping in salty water, you would imagine that the salt amount is going to increase. So let's put together some equations that can model this. So if we think about how much salt, so we're always going to think around conservation equations here. So we're going to think, well, obviously the amount of salt, for example, in x1, the rate of change of that must be salt in less whatever salt leaves. So when we think about this, our salt in is going to be determined by, well, this over here. So salt in, let's put salt in from the left, and we also got salt possibly coming in from the right, plus salt in from the right, and then we've got salt that's leaving, so that's minus the salt that's going out. And we could put together a similar thing for x2, which would say, okay, well, we've got salt coming in, but we've also got salt going out in two directions, so we'll do that as well. But let's finish up with x1. How much salt have we got coming in from the left? Well, we've got 0.1 kilograms per liter, and that's entering at 5 liters per minute. So that's going to give us a grand total of 0.5 kilograms per minute. So that's how much salt is coming in from the left. If we think about this flow coming into salt tank 1 from tank 2, how much have we got? Well, the rate is 3 liters per minute, so that's 3 liters per minute, and it's going to depend on how much salt there is in tank 2. So that's going to be however much salt there is divided by the amount of water. So that's because we're looking at how many kilograms per liter are coming in. So that's going to be x2 over 1000, and that's kilograms per liter. So that's the salt that's coming in from tank 2, and then finally we need the salt that's leaving. Well, that's leaving at a rate of 5 liters per minute, and oh wait, no, I'm not right, I'm wrong here. We need this bit over here, so that's leaving at a rate of 8 liters per minute. How much is leaving? Well, it's however much is in tank 1 divided by the volume of tank 1, so that's 500, that's kilograms per liter. So if we put that all together, we have a differential equation that looks like this. It's going to be, so I'm just moving this bit to the front, so that's a minus sign. Minus 8 over 500 is the same as 2 over 125 times x1, and then we've got plus this term over here, so that's 3 over 1000 times x2 plus this bit over here is going to give us a 0.5. So that's a differential equation that models how the amount of salt changes in tank 1. I would recommend that you do the same calculation for yourself, and you'll find that you get, for x2, you should have this. So things that you can look at to check that you're kind of thinking about things in the right way. You should have that the amount of salt that is leaving, because salt only leaves tank 1 to go to tank 2, should be the amount of salt that is entering from tank 1 into tank 2, which we've got over here. So you should be able to check that you've got things correctly, and there we go. And over here, this constant term in tank 1 makes sense because we've got just this constant amount that's being fed in. But we don't have a constant amount being fed into tank 2. Okay, so we just have two differential equations in two unknowns. So we could, well, we need to use a technique where we're going to try the Laplace transform idea. So if we do the Laplace transform, what do we get? Well, we have, for the first differential equation, we have s x1 of s, and then we need our minus x1 of 0 is equal to minus 2 over 125 x1 of s plus 3 over 1000 x2 of s plus 1 over 2s. So that's, we've just Laplace transformed x1 and x2, and our Laplace transform of a constant, remember, is 1 over the constant, and there's our 2 coming through. Now we've said that the amount of salt at time t equals 0 is 0, so this term is 0, and it's going to be the same for our second tank. So we're going to have s for x2 of s is equal to 2 over 125 x1 of s minus 1 over 125 x2 of s. And just to make it absolutely clear, we've got that big x1 of s is our Laplace transform of our little x1 of t, and x2 of s is our Laplace transform of little x2 of t. Okay. So here we don't have two differential equations that we're trying to solve. Now we just have two linear equations that we want to solve in two unknowns. So you just use MATLAB or whatever. So you can solve and if you do that, you will find x1 is equal to 5125 s plus 1 all over so things that look very similar to the Laplace transforms for individual differential equations that we were finding. And this is 100 all over s 100 s squared plus 300 s plus 1. Let's just add another page here. And we would use, and so now we've got the Laplace transform, an equation for the Laplace transform of our little x1 of t and a Laplace transform version of our x2. So we would use MATLAB, or if we felt like doing partial fractions, we would use partial fractions. And so we can inverse transform to get x1 of t is 50 minus 75 over 4 e to the minus t over 50 minus 1 to 5 over 4, and our x2 of t is equal to 100 plus 25 e to the minus t over 50 minus 125 e to the minus t over 250. And you could plot these, and I recommend that you do, and I'll put the plot into the final version of this. But you can have a look and see that what we've got is we've got a 50, and then we're subtracting off two terms that are exponential decay. So, and again over here we're starting at 100, and we've got a plus, so we're adding an exponential and then subtracting off an exponential decay. So we will get things that start at 0. You can check that they both start at 0 and then increase as they go. So spend a little bit of time with this because it'll help you revise Laplace transforms and also get a bit of practice, plot those two and see that they make sense. So there we go, Laplace transforms. We just get to use everything we spent a whole week learning in a whole new context that works really nicely. So just to kind of make a remark that's going to foreshadow when we talk about the matrix exponential. So we were using the Laplace transform to solve systems like this. And when we rewrite that, we could write our solution as our Laplace transform is equal to this thing over here, where this is the inverse of the matrix identity times S minus A. Now, if you think back to when we were solving an ordinary scalar ODE like this, our solution was, in scalar terms, it looked like this. It was x of s, f of s over s minus a. So we've got really an f of s times s minus a to the minus 1 plus x naught s minus a to the minus 1. So it seems like there's this kind of parallel going on. We've got the inverse of this matrix here, and we've got the inverse of the scalar here, s minus a. And again, same thing over here. We've got the inverse of this matrix here, which looks like this scalar over here. So, and we know that each of these scalars over here correspond to an e to the at. So if we were to just kind of look at parallels, we'd kind of wonder, could it be that this thing over here corresponds to something weird like e to the at, to kind of draw the parallels together? And in fact, it's going to turn out we can define the matrix exponential in such a way that this is the case, which is going to be kind of pleasing. But before we get there, let's just take some time. So here is a system for you to solve. Give it a go, and when you've tried it, come back and we'll talk through the solution. Okay, so hopefully you had a chance to work through this example. So the first thing that we do when we're solving a system, well, the only technique that we've learned so far is taking the Laplace transform of each equation. So let's do that. So the Laplace transform of the first derivative of x1 will be s times the Laplace transform of x1 minus the value of x1 at time t equals 0, which is a half, so that's going to give us plus a half. And then on the right hand side we have 3 times the Laplace transform of x1 minus the Laplace transform of x2 plus 3 times the Laplace transform of e to the t, which is just 1 over s minus 1. So this is going to give us a 3 over s minus 1. So that was our first equation. And our second equation, if we take the Laplace transform, we do the same thing again. So it's going to be s times x2. In this case, it's going to be minus a half is equal to minus Laplace transform of x1 plus 3 times the Laplace transform of x2. And just remember that each of these x's is a function of our kind of frequency type variable s. Okay, so we've gone from having 2 differential equations that we wanted to solve simultaneously by taking the Laplace transform. Now we just have 2 linear equations that we need to solve simultaneously. I would plug this into MATLAB, or Wolfram Alpha has a nice solver, or you could do this by hand. So we know that what we want to get is we want to get x1 in terms of s and x2 in terms of s, and if you do that, what you'll get is you'll get x1 is minus s plus 5 over 2 s squared minus 3s plus 2, and you would get x2 is s plus 1 over 2 s squared minus 3s plus 2. So now what we need to do is the inverse Laplace transform for both of those. And again, you could do this by hand. You could partial fraction these and then use the table to figure out what the inverse transform could be, or you could just plug it into MATLAB or your favorite software, whichever way around you want to do it. We're going to do the inverse. And what you'll find is that you get x1 of t is equal to 3/2 e to the 2t minus 2e to the t, and x2t is 3/2 e to the 2t minus e to the t. Okay, so notice that we've basically leveraged everything that we did with single differential equations and the Laplace transform to be able to pretty quickly solve systems of DEs which have some forcing term that's non-zero. Okay, so that's useful. And in fact, we can leverage our method of undetermined coefficients in much the same way to find a different way of solving systems. So let's have a look at how we might do that. So remember when we were talking about the undetermined coefficients method, what we said was, well, if we've got a non-homogeneous DE, we can form our general solution by finding the solution to the homogeneous case and then finding a specific solution to the non-homogeneous case. And we can do exactly the same thing when we've got systems of DEs. So we assume that we've got the non-homogeneous version that we're trying to solve. Let's actually use arrows. And then we think about the homogeneous version, and we've already figured out how to solve that. We did that last week. So we can use whichever method we like to do that. And then we claim that our general solution is going to be formed by our general solution to the homogeneous. So this is solution to the homogeneous, the general solution that is, and a particular solution to the non-homogeneous version. And you can do a quick check for yourself that if you plug an x of t formed like this into the non-homogeneous differential equation, a system of DEs, then you do actually find that it is a solution. It's the same basic idea. We did the same check when we tried this idea just for single DEs. But now we do the same. You can do the same check, but it's a matrix equation instead of a scalar equation. So the idea here is, okay, well, we know how to find our solution to the homogeneous system, so we just need some way of finding a particular solution, and then we're good to go. So how might we do this? Well, we use, as is no surprise given the heading up here, undetermined coefficients again. So remember, this was where we said, okay, we think that the particular solution is going to look kind of like the forcing term. So let's have a look at an example. So we've got our system where our A is 3 minus 2, 12 minus 7. So remember, we're thinking about a system like this. Okay, so this A is this coefficient of our x here, and our f here is this thing there. And we want to find a solution that has the initial data that x1 is equal to 1 and x2 is at time 0 is equal to 2. What do we do? Well, we look at this, which is our forcing term, and we say, well, this really looks like, I could do a slight rewrite here, it looks like e to the minus 4t times the vector 1, 3. And if you remember, when we were thinking about forcing terms that looked, for example, like 6e to the minus 4t, then the solution that we tried, we would try a solution that looked like a e to the minus 4t. And then what we wanted to do was we wanted to find the value of that constant. So what we're going to do in this case is exactly the same, except we've got an e to the minus 4t here, which is the same, but what we've got over here is a vector of constants. So instead of just finding a scalar, when we're doing this for systems, we're going to say, well, we want to find some vector, which when I multiply it by e to the minus 4t, is a solution to the dE. So we're going to try an ansatz of the form, how am I going to write this? I'm going to call it my particular solution is going to be e to the minus 4t times some v. And this v is the thing we want to find. This is the constant vector to find. Okay, so we're using exactly the same method that we did for single dEs. Now we're just having to find a constant vector instead of just a constant scalar. Alright, and we do the same thing that we did. We just substitute our particular solution into our dE and see what we can find. So let's substitute our particular vector into the non-homogeneous version. So what do we get? Well, we need to take the derivative. So this, remember, is our non-homogeneous dE. So we need to have the derivative. So I've got a minus 4 e to the minus 4t times v must be equal to, and then we've got over here we've got an a times x, so we've got an e to the minus 4t times a times v plus, and now we've got plus f, so that's plus e to the minus 4t times 1, 3. Okay, so what do we do next? Well, we're going to divide through by e to the minus 4t, which is never equal to 0, and I'm going to bring this term over to the left. So I've got minus 4 times v minus a times v is equal to 1, 3. Now a little bit of rewriting. I'm going to multiply through by minus 1 just to make things a bit easier. And I'm going to look at this term over here and rewrite that as 4 times the identity matrix times v. So we can always multiply by the identity matrix, just like we can always multiply through by 1. So that will give me a 4 times I times v, a times v is equal to minus 1 minus 3. And now that I've got a matrix here and a matrix here, I can factor out my v. So I've got a 4i, and that should be a plus a times v is equal to minus 1 minus 3. And ideally what we'd like to be able to do is to multiply on the left on both sides by the inverse of this matrix here. But the question is, does this have an inverse? And well, you could just try and calculate the inverse and see whether it works or not. That's one way. Another way would be to have a look at the eigenvalues of A. So the answer is yes, it does have an inverse. So the eigenvalues of A, if you have a look at those, are minus 1 and minus 3. So if we think about what would it mean for this not to have an inverse, that would mean that we have, so this thing looks like a11 plus 4, a12, a21, a22 plus 4. So that's what that looks like. And if this thing didn't have an inverse, that would mean that minus 4 would have to be an eigenvalue of that matrix. It would mean minus 4 is an eigenvalue of A itself, because we'd be thinking of this as our minus lambda. So if we looked at this and said it's not invertible, then we would have to have a case that minus 4 was an eigenvalue of A, but we know that it's not because of this here. And we just worked out magically using MATLAB what the eigenvalues were, and minus 4 wasn't one of them. So it's minus 4. So we multiply both sides of the equation on the left by the inverse, and what we end up with is our v is equal to our inverse times minus 1 minus 3. And let's just write this out explicitly. What we've got is a11, so what have we got? That's 3 plus 4 minus 2, 12, and minus 7 plus 4, so that's minus 3, all times minus 1 minus 3. And if you work that all out, you will end up with minus 1 minus 3. Okay, so we have found our v. So what we've found here is that, if you think back to what we was doing when we started off here, we tried to find some constant vector v so that e to the minus 4t times this constant vector is a particular solution to our original differential equation. So after all that work, what we found is that our particular solution that we're interested in is e to the minus 4t times minus 1 minus 3. So putting this all together, we can now have a general solution to the non-homogeneous version. So we get that our general solution to our non-homogeneous differential equation is e to the minus 4t times 1 minus 3, so that's our particular one, plus the general solution to the non-homogeneous to the homogeneous version, which you could have worked out the way we did last week. It looks like this. Okay, so we've got our general solution, and then if you want to find the specific solution, so we want a solution with initial data, you plug that in. So let's substitute that our value of x at 0 is 1, 2. You can plug that in to get that c1 is equal to 1 and c2 is equal to 1 as well. So finally we can end up with the specific solution to the non-homogeneous case with the initial conditions that we got be okay. So this is just a different way of solving systems. We've now seen two. So we saw the Laplace version where you just take the Laplacian, and kind of there the trickiness comes in working with the algebra from the Laplace transformed equations that you solve simultaneously, and then finding the inverse Laplace transform. An alternative method that we've just looked at now is our method of unknown coefficients, where the trickiness is really finding the particular solution, which requires that you kind of make a guess, substitute it in, find out what the coefficients are, and in this case it's finding a vector. Previously it was just finding a scalar. Once you've got that particular solution, it's pretty straightforward. You use the general solution to the homogeneous version, add your particular solution, and away you go. So each version has its own kind of trickinesses and it has its own merits. The thing to note, obviously, about using the Laplace transform is we know that the Laplace transform works perfectly well with discontinuous forcing functions like Dirac deltas and Heaviside, whereas this version that we've looked at here, we can only really have continuous forcing functions because we're using those as our ansatz for our particular solution, and they have to be continuous from the theory that we did last week or the week before. But nonetheless, so this is another technique. And we're going to look at one more. The reason we might look at, we're looking at the matrix exponential is because not only is it useful in solving differential equations, but it comes up all over for sort of any further physics that you might want to do. So having seen the matrix exponential is a really useful thing. So I thought doing it in this context would be helpful. So we talked a little bit about why we might want to do something crazy like this. When we were thinking about our scalar ODEs, our homogeneous scalar ODEs, and we saw that we have solutions of the form some constant times e to the at. And we saw that the same thing happens if we use the Laplace transform. So that was just for scalar, a single differential equation. But with constant coefficient systems, where we're looking at the homogeneous version, we saw when we looked at the Laplace transform method of solving this, that we end up with something quite similar. So in our Laplace transformed version of the solution, we got this. In our Laplace transformed version of the scalar, we got this. And this, if we inverse Laplace transform, gives us an e to the at. So the question we might ask is, well, if we take the inverse Laplace transform of this matrix thing, do we end up with something like e to the at? It would be very nice if there was this kind of parallel, although it's not immediately clear what this thing could be, because it would need to be a matrix. And we don't know what the exponent of a matrix, an exponential raised to a matrix is. But it turns out to be really useful to be able to define that in a way that makes all this work together. So we have this crazy thing that the matrix exponential e to the ta is defined as an n by n matrix with entries that are functions of t. So even though we're writing it as e to the something, this is actually going to be a matrix. And it is furthermore going to satisfy the kinds of differential equations that we're interested in. So let's have a look at this in a little more detail, because it sounds crazy, but it might just work. So we start by thinking about the Taylor series for e to the t, which I hope you've seen before. So this is just straight all scalars, e to the t, and we can expand that as 1 plus t squared over 2 plus t squared over 3, which is, over 6, which is 3 factorial. In short, the Taylor series for e to the t is given by this thing over here. And it turns out to be really useful to define, so notice this is a definition, there's nothing natural about it, it's just we're choosing to define it this way because it works well. We define e raised to the power b, where b is a matrix, an n by n matrix, as, and we use the same idea here. So here we had 1 plus t squared over 2, and here we're going to have e to the b is the identity matrix plus b plus matrix b squared over 2 plus b squared over b cubed over 3 factorial, and so on. So we get virtually the same looking thing for our definition of the matrix exponential. But notice that this one is definitely a scalar, whereas over here we've got an infinite sum, and each term is a matrix. It's some power of b divided by k factorial. So that's what I've just said over here. If we're looking at a few points, b to the k is an n by n matrix. So every time you're adding an n by n matrix, you're going to end up with an n by n matrix. And just, and if we think about not taking the so this goes up to infinity. If we just take up to some m, then if we take the first m terms, we're always going to end up with an n by n matrix again. So we can think about, and it's going to be useful to have defined Sm, which is the sum of the first m terms in our kind of matrix Taylor series. And this gives us a way, just as we have, so here we could write that e to the t is the limit as t goes to infinity of, sorry, not as t goes to infinity, as m goes to infinity of this thing over here. So instead of putting our infinity here, we could say, well, e to the t is what happens when we take the finite sum here and let the finite, the end of the sum go to infinity. Doing the same thing, what we'd like to have, where we want to head with this, is be able to say that the limit as m goes to infinity of our Sm is equal to our e to the b. That's kind of what we're hoping. So the idea is basically, when we're saying this, is that if we take enough terms, so we let m be big enough, then we're going to approach this thing that we want, this matrix exponential. So point 3 here is really saying it's not obvious that this is the case, but it turns out that it does. We can always do that, so that this is the right definition for the matrix exponential. Let's just look at a little bit of an example here, so that you can start to see how these things go. So if we have a look, so we're going to look at different values of m and see where we go. So if we look at S1, that's going to be the sum from k equals 0 to 1 of b to the k of the k factorial. So that's going to be b to the 0 plus b to the 1 over 1. Now we're defining b to the 0 as the identity matrix, just like we have anything, any scalar raised to the power 0 is 1. So we've got the identity plus b, so that's going to be equal to 4 minus 2, 4 minus 2. Okay, let's take another term. So if we have a look at S2, so that's going to be these two terms plus, and now we need b squared over 2, and you could plug this in to MATLAB, or you could multiply out by hand, and if you did, you would find that this was 9 over 2 minus 2, 4 minus 3 over 2. And you could keep going, and if you have a look in the textbook, they give some more examples, but if we go up to S10, that's going to be approximately equal to 5.069, 4.700, minus 2.350, minus 1.983. And as you keep adding terms, you'll see that the difference between successive sums gets smaller and smaller. So just, and this is not a rigorous proof, but just because we took some random matrix and we started calculating terms in the matrix exponential, and it seems like it's converging. It seems like maybe in general it does, and in fact in general it does. So that's nice. So this seems to converge. Generally speaking, we're not going to use the Taylor expansion the way we did here. In order to calculate the matrix exponential, you would just plug it into a computer, and there are faster algorithms, but we're not going to talk about those. So computers are super useful here. If you want to find the matrix exponential of a given matrix, you just plug it into the computer. What does this mean? This means that we can essentially define our matrix exponential in terms of the Taylor series, the way we've just been kind of discussing before. So we end up with this final definition of the matrix exponential of a given matrix B as the matrix where we get each component as we did here by taking the Taylor expansion, this thing over here. So this might seem slightly weird. We define e to the b in this way in terms of the Taylor expansion, but generally in calculating it we don't do that. And this is actually the same as working out, for example, e to the x. We would define it in terms of the Taylor expansion, but when you're actually calculating it, there are quicker ways of calculating it. So what are some of the properties of this crazy matrix exponential? Well, the good news is it behaves almost exactly like the scalar exponential that we know, which is great. So for example, the matrix exponential of the zero matrix is the identity matrix, which is great because remember we have e to the e to the 0 is equal to 1 when this is the 0, this is a scalar. So we would like to have the same parallels, and we've got them over here. We've got e to the 0 matrix is equal to the identity. If we have the case that two matrices commute, so it doesn't matter which way you multiply them, and remember with matrices this is not a given, but if it is the case that they commute, then we can say that e raised to the b plus c is the same as e to the b, e to the c. And this is the same as our scalar situation, e to the a plus b is equal to e to the a, e to the b. The only important caveat here is that you need to have that bc is equal to cb. So if that's not the case, then this is false. So that is a difference between the matrix exponential and the normal exponential, because normal exponential a plus b is always equal to b plus a, and a times b is always equal to b times a. So we don't have that issue. So this one is a little different. We know that for our scalar exponent we have e to the a times e to the minus a is just equal to 1. And the good news is that for our matrix exponential we have the same thing. So e to the b times e to the minus b, where b is a matrix, is going to give you the identity. What does this tell you? This tells you that the matrix e to the b is always invertible, and the inverse is e to the minus b. So that's a useful thing. And finally, we have this identity over here. B times its matrix exponential commutes with e to the b times b. And you could go back to the definition of e to the b to see why that is. So we know we've got this definition over here, e to the b, and if you can imagine, you just multiply by b all the way through, then you could take the b out on this side on the right, and you'd end up with the same equation. So that's how that works. So what has this crazy definition brought us? Well, we want to use our matrix exponential to be able to solve systems of DEs. And in order to do that, we're going to need to think about not just e raised to some constant matrix, but we want to have variables in our exponent. So we're defining e to the ta, so here t is our variable, well, we're just going to let b be ta in our definition, and so what we've got is that e raised to the power t scalar times a matrix is this thing over here. So we've just plugged in ta for b's. How does this help? Well, if our matrix is A that we've got here, then it can be shown that, and we're not going to go through it, but by either tediously working through the Taylor series or using a computational technique, you can show that e raised to the power t times a is this thing over here. So as the note says here, you could do it using the Taylor series. It's just not a lot of fun. We're not going to have a look at how to perform this later in the section. You can read the textbook if you want to. Usually you're just going to say, computer, please do it for me. So the key thing here, though, is that we know how to, given some matrix, A, we can form E, the matrix exponential e to the ta. So in order to be able to use our new matrix exponential e to the ta to solve differential equations, we're going to need the derivative, because differential equations have derivatives. So let's calculate that. So we're going to use the Taylor sum that we've defined our e to the ta. So we need d by dt of, so this is k, sum from k is equal to 0 to infinity of t to the k, e to the k over k factorial. So this is just a sum of terms. So we've got the derivative of a sum, which is the same as the sum of all the derivatives. So we can take our derivatives in. So this is going to be a sum from k equals 0 to infinity d by dt, t to the k, a to the k over k factorial. Now, our a to the k and our k factorial are all just constants. So the only term that really gets differentiated is our t to the k. So we want the derivative of t to the k with respect to t. We know how to do that. So we've got k times t to the k minus 1 times ak over k factorial. And this is only, we don't have a k equals 0 term anymore, because when we take the derivative, we only go as far as 0, so t to the 0, which is 1. So we've got from k equals 1 to infinity. So our k equals 0 term drops out. And now we can do a little bit of rewriting. So you know that k factorial is k times k minus 1 times k minus 2 and so on. So we've got a k in the denominator and a k in the numerator, so we can cancel those and rewrite. So we've got k is equal to 1 to infinity t k minus 1 a to the k over k minus 1 factorial. And now we're going to do something a little cunning. We're going to say let j equal k minus 1. What is that going to give us? Well, let's have a look. It's going to give us, so we're replacing, so when k is equal to 1, then j is equal to 0. So we've got from j is equal to 0 to infinity. T to the k minus 1, so that's t to the j. A to the k, so that's going to be j plus 1 over j factorial. And you'll see that this looks almost like this bit over here, except we've got a j plus 1. So writing this out just once more in excruciating detail, I've got a t to the j, a to the j times a over j factorial. So I can pull this a out, and then what I end up with is a times the sum. But this sum over here, although it has j's instead of k's, is exactly what we use to define e to the ta. So what we've ended up with is that this is equal to a times e to the t times a. So we did all that work to just show that the derivative of e to the ta is equal to a times e to the ta, which is kind of exactly what we would hope, because if you remember from scalars, if we had e to the ax and we took the derivative, that's just equal to a e to the ax. So we can see that our definition of the matrix exponential is behaving exactly like we would like it to, and we can use these analogies with the scalar version. Okay, also now we have the derivative, we can use this to solve differential equations. How do we do that? So we're trying to solve homogeneous differential equations of this form with some initial conditions for any square matrix A and any initial conditions that we like. So that's our goal. We've defined, so what we're going to do is we're going to define this big X, not to be confused with our Laplace transform. Okay, so that was a scalar big X, this is a matrix big X, and it's defined as the matrix exponential e to the ta. Okay, so it's a matrix. And we can show that this matrix, which is called the fundamental matrix solution, satisfies this differential equation over here. And we know that because we've just shown that the derivative of this thing over here is a times the original thing, which is basically, we just showed this over here. But we've now suddenly got a matrix that we're saying is a solution to the differential equation. How does that solve our problem? Well, we're thinking about this matrix as consisting of a bunch of columns, an x1 and x2. So we're thinking of a whole bunch of columns. So what we're really saying when we write this matrix equation over here is that this column here satisfies the equation x1 dot is equal to ax1. This column solves this column solves this. So each individual column in our fundamental matrix solution is a solution to this differential equation. And we know that if we've got a whole bunch of solutions to differential equations, then any linear combination must also be a solution. So what we get out of this is that if we have our fundamental matrix solution, then we take the columns and we make a linear combination of them, like this over here. So we've got a linear combination of the columns. That is going to give us our general solution to the homogeneous system of DEs. And once we've got that general solution, then we can plug in our initial conditions and we're good to go. So let's have a look at how that works. So if we look at our fundamental matrix solution, so that's this thing over here, defined by this. If we put in 0, then we've got e to the 0 matrix, which we know is the identity. So our initial condition for the fundamental matrix solution is 0. So in order to construct a solution which has something that's not 0, all we really need to do is take whatever our initial solution, our initial condition is, and use those as our constants in our general solution that we had over here. So it's super simple. It's even easier than we've seen before. So you look at your initial data and you use your initial data constants to be the constants which you multiply each column by to get your general solution. So we've done quite a lot of technology and new stuff, but what does it all boil down to? It boils down to saying that you can use the matrix exponential to solve homogeneous DEs with the initial data and you can go straight ahead and write down the solution, which is going to be matrix exponential of your matrix here times by your initial condition. So that, although there's kind of a lot of stuff going on with the definition of the matrix exponential and understanding all of that, this is quite possibly the easiest way of solving a homogeneous differential system of differential equations. But you can also use the Laplace transform as we've seen, or undetermined coefficients. So now we have 3 different ways of solving these, and you've also been introduced to the matrix exponential. So let's just work through one example to see what this looks like in practice. So I said without proof that, way back over here, let's see if I can find it, said we can show that if a is equal to this thing over here, then e to the ta is this. And the easiest way to do that would be to plug it into to MATLAB. So we know that e to the ta is equal to minus 3 plus 4 e to the minus t, 2 minus 2 e to the minus t, 6 e to the minus t minus 6, 4 minus 3 e to the minus t. And by what we've just discussed, we know that this is one solution and this column is another solution. So we take the linear combination and that would give us a general solution. But we also just discussed that if we want the specific solution with this initial condition, then we form our final solution as x of t equal to e to the ta times 1, 3. And if we do that multiplication, what we end up with is 3 minus 2 e to the minus t times 6 minus 3 to the I minus t. So if you have some quick way of calculating the matrix exponential, then solving DEs of this form using the matrix exponential is just the most straightforward, the quickest method. The thing to kind of be aware of is that there's a lot of understanding that needs to go into why this is a solution. What I would recommend that you do, just so that you get some practice, is you solve this differential equation in all the possible different ways that we could, and make sure that you get the same answer in all cases. So it's worth looking at another example. So if we were looking at our critically damped mass spring given by this, then we could use the method that we found for converting the second order into 2 first orders. So as usual, you take x1 to be u, x2 to be the first derivative of u, convert it into 2 differential equations, got a system of differential equations, and you would find that the matrix that you have in your system looks like this. And if you check this, because we know that if we're solving a homogeneous system, we need to find the eigenvalues, check this and you would find that this has eigenvalues lambda is equal to minus 2. Is going to be a double eigenvalue, so it's the same roots, and the only eigenvector that you can find is minus 1 and 2. And this would then be kind of annoying because we'd have to use that technique that we did at the end of last week, which is where you find some other eigenvector so that you can form your general solution. And that was all a bit cumbersome and annoying. But the matrix exponential actually gives us a very nice way of doing this pretty quickly. So you would need an alternative vector using previous method. But using the matrix exponential, what would we get? Well, you would plug this into MATLAB to get that e to the ta is equal to 2t plus 1 e to the 2t t e to the minus 2t minus 4t e to the minus 2t minus 2t plus 1 e to the minus 2t. Okay, so I would not expect you to be able to calculate this in a test or exam. You would plug this into a computer in real life. And then we just go straight ahead and form our solution using this, which is that x of t is equal to e to the ta times, so well, let's say with initial conditions so if, I don't know, 1 minus 5, our final solution would be this, which is so having the matrix exponential means that we don't have to worry about the eigenvalues quite as much because it works either way. We don't have to do the eigenvalue calculation in order to solve things and figure out whether we have repeated roots or anything like that. Matrix exponential just straight away gives us the solution. So one thing to do would be to solve this problem in the way that we did at the end of last week. So without the matrix exponential, so finding a second vector to put into your general solution, and then use the matrix exponential and check that you get the same answer. Things have changed quite a lot in the last sort of 20 years because we have computer systems that will easily find the matrix exponential. So this calculation where I just said plug it into MATLAB used to be really tricky, so it used to make more sense to use the previous method because finding eigenvalues is a little bit easier than finding the matrix exponential. But now that we can easily find the matrix exponential, no reason not to use this as well. That said, it still becomes really important to know about the eigenvalues because, as we saw, the eigenvalues tell you a lot about your answer. They tell you whether it's oscillating, decaying, growing exponentially, maybe there's no exponential decay or growth. So we still tend to do quite a lot of eigenvalue analysis, even if the way we solve things has changed slightly and we use the matrix exponential. A few final things to say. So we've done a huge amount, and I haven't gone into a huge amount of detail about everything, but I hope I've given you an overview of differential equations and systems of differential equations, and I hope that you can see the parallels between how we solved individual differential equations and then using matrices found many parallel ways for solving systems. And there's a lot of really beautiful mathematics that ties together far more rigorously than we've done why these techniques are so similar. What's kind of relevant if you're going to go on with physics is this idea that our solution, if we're thinking about just a scalar ODE of this form here, our solution here is really a prescription of how our initial value our x naught is evolved over time. So it's kind of evolved by this e to the at. So either increasing or decreasing, whether a is positive or negative. And our matrix exponential really has the same kind of idea in it, in that we start with an initial value of x0, and then our matrix, our time-dependent matrix e to the ta, says how that initial vector evolves over time. And this idea of having some operator, so we're thinking of this time-dependent matrix as an operator. It's something that operates on an initial state. And this idea is so prevalent in physics, particularly, for example, if you're looking at quantum mechanics, you've got operators, you've got in classical mechanics, you've got Hamiltonians, things like that. This idea that you have some initial state and then some matrix that operates on that initial state and evolves your system in a specific way. So I hope that you'll also take a little bit out of this course, this idea that somehow we can use time-dependent matrices to explain the evolution of dynamical systems in a very general way. Okay, so we've now finished the coursework for this differential equations course. I hope that you've had fun. There is no final exam, there's just the midterm, as you know. And I think the key takeaways out of this course, on the one hand, are that there are techniques that we've learnt for solving DEs and systems of DEs. But I hope what you've also got a little bit of insight into is a lot of what we do when we're solving differential equations is we make a lot of use of computers, and there are lots of ways that you can do that. Alright, so make sure that you're comfortable with this material and also have fun doing your project, and I look forward to seeing you hopefully in some other maths course.